Obrigado. Mas vou falar em inglês. Acho que eu já preparei em inglês. Okay. First, I would like to thank the organizer for inviting me to give the talk. As Professor Ketch mentioned that I changed the title, but actually it's the same. So I will talk about the rich solitons, which is not a new topic, but in the recent years it increased very quickly. And in the April of this year, there was a conference on rich solitons in Pisa, Italy. So there are many people working on this problem. So first, I will give the plan or the outline of my talk. In the first part, I'll give some definitions and some fundamental facts. And then I will talk about examples, some examples, most important examples in this area. And I separate the part, which classification of three-dimensional gradually shrinking solitons, which is very important in the proof of Poincare conjecture. And then I will go to high-dimensional case for the classification of the gradual solitons, especially on shrinking and steady. If I have time, I will give a small part of the proof of the theorem in section 3. So in the final part, I will talk about, if I have time, some further questions. Okay. So what is rich soliton? Rich soliton is a complete remainder metric on a smooth manifold. And if you have a smooth vector field such that the rich tensor satisfies this equation, where rho is a constant. So in a special case, when the V is the gradient of some function, so we call it gradient soliton, gradient rich soliton. Usually we call it gradient soliton sometimes. So here we have a function. This is a Hessian of the function. This is a Lie derivative of metric. So the rich curvature plus the Hessian of the function equals to this. And we have three cases. If rho is 0, we call this soliton is steady. And if rho is positive, we call this shrinking. And though rho is negative, we call it's expanding. And in special case, if f is constant, this is 0. This is just the Einstein metric. Okay. So it is important because of some reasons. Principally, for us, it's come from the rich flow. When you study the singularity, it naturally appears. And of course, it's a special solution of the rich flow equation. So also, it is closely related to Hanake inequalities, which has been studied by Liao, Hamilton, and furtherly Perelman. Also, it is quite similar to many problems of variational problems. So if you look at the Perelman's functional, it is critical point of the functional. And so when it is critical point, you can study the stability. So actually, the recent work of Coding and Minikos, they studied a similar problem for mean curvature flow. They classified the generic singularities for mean curvature flow. So we can ask the same question. So it is important when it is stable. It just means that the critical point, if you perturb it a little bit, it will, after some time, the flow will go back to this point. So this is for rich flow. Also, it's of course, it's a natural extension of Einstein manifold. When you study the topology of a Riemannian manifold, it's convenient you find a good metric. For most of the case, you're looking for the Einstein metric, but sometimes you don't have Einstein metric on some manifold. So in this case, you can try to find the gradient soliton such that you can study the topology in some problems more easily. Another field, there are many people has studied a lot, is the smooth metric measure space. That means you have a measure, then you have a Berkeley rich tensor. So I will not have time to explain this in detail. Now we can see some examples. Before that, I would like to mention a fundamental result of Hamilton, which proves that if you, for the gradient soliton, the scalar curvature and the potential function satisfy this equation, where C is a constant. Rho is the constant of the gradient soliton. So if you change F, the C can be chosen to be 0. So actually, we usually call this normalization of the potential function. Of course, you can choose another way. C different than 0. For example, you can choose the weighted volume is 1, and the C may be not 0. But you always can choose C is 0. So Hamilton and Ivy proves that on compact manifold, a gradient steady or expanding rich soliton is necessary Einstein metric. So in the compact case, you don't have rich solitons other than Einstein manifold. So this result is for gradient soliton. Actually, if you use after that Perelman proved that in compact case all the rich solitons are gradient. So actually, combined with the Perelman's result, you have any compact steady or expanding rich soliton must be Einstein. So in the compact case, you don't have new examples. And also in the shrinking case, the Hamilton and Ivy proved that for 2-dimensional and 3-dimensional case, there is all the compact shrinking rich soliton has to be of a constant positive curvature. From this, we have a table that if you look at gradient soliton. So if you look at the compact case, so you only have so n equals 2, 3 is okay, and steady and steady and expanding. It's okay. So the remaining case are shrinking case for n bigger than or equal to 4, or non-compact case. Actually, a non-compact case is very important because it arises naturally in the rich flow. When you are dialecting, the limit has to be compact, non-compact. So the first non-trivial example was found by Detang Zhou and Koisu on the complex surface, complex surface. They construct the gradient soliton, gradient shrinking soliton on this manifold, and actually they can this construction can be generalized to high dimensional case. Yeah. And also Xujia Wang and Xiaohua Zhu found a gradient Kelly-Rich soliton on this manifold. CP2 connects some with 2 copies of CP2 with the opposite orientation. So they construct the new examples. Actually, they prove that the more general case is for phonotoric varieties of complex dimension bigger than or equal to with non-vanishing Futaki invariant. That means you may don't have Einstein metric, but you have a rich soliton. And for non-compact case, the example was also used Kelly structure. They find a complete non-compact shrinking gradient Kelly-rich soliton. Kelly-rich soliton means you just besides this rich soliton, it has a Kelly structure which is compatible. So this example is important because it has, we will see it later, it has positive scalar curvature, but the rich curvature does not have a fixed sign. That means the shrinking soliton, rich soliton behaves very similar, in some sense similar to positive curvature case, but now you have rich curvature is not non-negative. You don't have, it does not have a sign. I will go back later. So for the status soliton, the first, the Hamilton found which he called a cigar. Actually, it takes this same cigar is at infinite. It's just like a cylinder. It's asymptotical to a cylinder like this. So the metric can be written down as this. And also, for high dimensional case, Robert Brown classified all the rotational symmetric status solitons. They have volume goes like this, and the diameter of is just like this. So it is important thing. Also, there are some new examples was found by Detang Zhou, and he using the complex structure, and also this is a constructions. I think I don't have time to go to in detail. And on CN, they can construct like this. Also, another kind of you just take a blow up of CN, the complex towers in our region. So the idea comes from the construction of Calabi and Iguchi Hansen. So this is for steady. And for expanding case, also by Huaidong, how they construct the examples. Since actually this is my talk is for grand rich solid. Actually, I will principally concentrate on shrinking and steady cases. So you can also construct using the word product or double word product, actually triple or so. Here is more examples. I just mentioned that this guy. So I cannot conclude with the example without mentioning the special examples of Gaussian solitons. This is a special case. So if you have a standard metric of Euclidean space, it can be shrinking, steady, and expanding. So if you choose this potential function, just like come from the heat kernel, you have this. So this is a shrinking case because reach is 0, the Hessian is half of the metric. If you choose the minus of this one, it is expanding. Of course, if you can choose f is 0, it's a standard solid. So this is a very special case. And this is similar special, but after that we will see that actually this f is not very it's not very so special. I will say. So the classification, I just mentioned some principal result of the line of the classification of three-dimensional gradient shrinking solitons. So this lemma is proved by Perelman is technically important during the proof. He proved that for the non-compact gradient shrinking soliton with bounded ridge curvature, which satisfy, of course, I take this is a shrinking equation, and this is normalization. Take this. I just normalize the constant is 1/2. Actually, it's not essential also. Perelman proved that you have constants, C1, C2, the small C1, C2, such that the potential function bounded below by the 1/4 r squared, something like that, and less than some constant plus this. And the gradient grows at most linearly. So for the proof of Poincare conjecture, in a singularity, it is automatically satisfied. But for the classification in three-dimensional, for the classification of gradient soliton, it's not a natural one. So okay, so let's see. Using this, Perelman proved this theorem. So, if you have a complete non-flat three-dimensional gradient shrinking soliton, suppose you have bounded and non-negative ridge sectional curvature. Actually, this implies the curvature operator is bounded, and it's kappa non-collapsing for all scales. So then, in this case, Perelman showed that the gradient ridge soliton has to be S3, or this case is compact, or its quotient, or cylinder. I mean, here it's non-flat, so there is no R3. So only these two cases. So they can classify this case, but it's sufficient for the proof of Poincare conjecture. because the kappa-long collapse also can be satisfied. But after that, people start to try to move this condition. It has been done by Lee and Waller. They remove the condition, the kappa-long collapse. So they prove that if you have also they only use the non-negative ridge curvature, but they don't need the bound, but they need the curvature tensor is bounded from above by exponential function. So of course they start with non-compact case. It's all it's a question. I should not put a non-compact here. But if it's non-compact, only this case. Then. So, in three-dimensional cases, they use this. That is why I mentioned that the example is important, because if you don't take the dimension into account, you only look at the equation, you cannot, you don't know if Rich is, actually you cannot prove that Rich is non-active. But fortunately, in three-dimensional case, first proved by Bin-Long Chen, that in three-dimensional case, if his proof can be used for high-dimensional case also. If you have Y tensor, vanished Y tensor, then for the shrinking soliton, the curvature has to be non-active. So in three-dimensional case, the Y tensor is 0, so automatically you have curvature non-active. So that condition can be removed. And then they can prove that because I just put here, the Hamilton proves that minus f equals to, I just put this. So if you have a control of this, you have this inequality. So if the curvature is non-active, all the sectional curvature is controlled by f. So the condition of the growth condition of this is automatically if you have it's just like the result of if you have, for example, just like this R is a distance function. So if you have this of course is controlled by this kind of stuff. So the key point is to prove that non-active ridge curvature. Also for now I forgot to mention. Now I will move to high-dimensional case. I will go back to prove this theorem with several lines, because it's a non-process. But finally, if you find a right way, the proof is not so complicated. So for high-dimensional case, Lee Waller also can use their tools with more computations, and they can prove that with this curvature growth, they can prove give a classification with the assumption of locally conformally flat in high-dimensional case. So they can classify the soliton, the gradient soliton like this. Also, the Peterson and Wiley change this condition to this. So for the as I mentioned, if the Y tensor is 0, what is the curvature? So that the Zhu Hong Zhang showed that for high-dimensional case, a compact gradient shrinking soliton with vanishing y tensor necessarily has non-negative curvature operator. It's quite strong. And consequently, the curvature grows at the most quadratic with respect to distance function. Using this, they can combine the result of the Wallach or Peterson-Wiley. It proves that for gradient shrinking soliton with vanishing y tensor must be a finite quotient of sphere or Sn minus 1 cross R. We will see that it's natural to ask why you don't have S1 cross something. I will explain it later. And another result is Kurzweil showed that classified all the rotational symmetric shrink soliton on the here is topologically sphere, Euclid space, and this cylinder, one-dimensional cylinder. Another result, without assuming the conformally flatness, it was this label proves that if the manifold is non-flat and with bounded and non-negative curvature operator is isometric to finite. Actually, it proved several years ago when we use, if you know the trick of Bohr-Wilken and the proof of differential sphere theorem of Brand and Schoen, this result can be proved another way, maybe simpler, because you're assuming the non-negative curvature operator. So I will repeat the important fact is that the non-negative curvature operator is automatically satisfied when n is equal to 3 and when all the shrinker is not conformally flat. So however, you don't have this if you don't assume the conformally flat. So this the example says that. So what we can do? So we need to study or estimate without assuming the positivity of the curvature. So here is some basic point we need to use. Firstly, is the binomial proof that we don't have non-negative rich curvature, but we always have non-negative scalar curvature. So if you have a point that the scalar curvature is 0, so the manifold, the soliton has to be flat. So if it's not identical to 0, it's positive. Another result is Huaidong Zhou and Xiping Zhu prove that if it's non-compact, you have an infinite volume. It's something natural, but we are expecting the better estimate. We don't know how to prove it. Huaidong Zhou and I proved that I'm not repeating, just for convenience, I put this here with this normalization. Without the curvature condition, we can prove that the potential function behaves exactly like the Gaussian shrinker with these two constants equal. So if you take here R is distance function. If you take a square root of f, twice of square root of f, it's just like asymptotically like a distant function at infinity. So here the constant only depend on the base point of and the curvature on small ball, fixed small ball. So this just I mentioned that the Gaussian shrinker is optimal, and also we can take this rho. We just put rho. Rho behaves like the distance function, and further, the gradient of rho is just less than or equal to 1. So from this and this equality, we also have this estimate of a scalar curvature. Another thing important, if you want to justify this equation, this condition is finite, so you also need the information of volume growth. Fortunately, we can prove that without the curvature condition, the volume growth grows at the most Euclidean. So this implies if you have a sign of rich curvature, it automatically is finite. So you can do an analysis problem on the gradient shrinking soliton without the additional curvature conditions. Okay. Again, the estimate is optimal, and actually, Calino and Lely prove that if you have a rich curvature, if it's non-flat, rich curvature non-negative, the limit has to be 0. Okay, so now we are ready to give a quick proof of the classification of the result of the classification of three-dimensional shrinking soliton. So we just pay attention to this equation. This equation is the curvature. If you have a rich flow, the curvature tensor just involves like this one, and the things that where P is like this. Lambda, mu, and nu is eigenvalues of rich curvature. We are now in three-dimensional case. This is has been proved by Hamilton, and it seems complicated, but we need to reorganize it. If you put in the situation of shrinking soliton, you just maintain this. You just change this term by this term using the f. So if you look at this term and this term, they have the same sign. This means the pinching of the eigenvalues of the. If you control this, you can control the pinching of eigenvalues of rich curvature. So I just rewrite this equation. Just put this is a term, and just put it like this. So I just put this term just called the u, and eta is this. Q is the non-positive term of this that I just change the sign here. So that equation can be written as this term. So it's quite simple, because before that it's quite complicated. Now you can see the essential things more clearly. So for this equation, it's a routine. You just take a compact supported function. You just do some computation. Because it's non-compact manifold, you have to take this supported function. So after some trivial computation, you arrive at this. So what means this term? So if you put this term, if you put this negative term on the other hand, so that means this term is controlled by this term. So if you choose the row like this kind of function, R to R. So when you increase it R, you will increase this term, which is less than or equal to this term. And this term is supposed to be decreased because you put the regions go to infinite, provided you can prove this is integrable. U square at. U square at means the combination of scalar curvature and E minus E to minus F. So you don't need to justify it if it's finite. So fortunately, using the estimate, we obtained and the non-negative curvature condition of the result of binomial chain. You have this, you control this, and you control this. So finally, you have volume growth. You have scalar curvature. You can control the scalar curvature. You can control the curvature operator. You have volume growth. Then you can prove that it's finite. So that finite means that the gradient U is 0. So the gradient U is 0 means this is constant. So from this is constant, also this is constant. Also, you have Q is constant, is 0. So Q is 0. You have this is 0. This is 0. So you just do analyze the case. You can prove that all the three terms are equal, or one is 0 to other terms are equal. So you can get a classification of three-dimensional case shrinking solid. So the proof can be simple. So the estimate can be used to study the case when the manifold is not conformally flat. It has been used by Montealo and Susan. They prove that this condition is automatic. This equality is automatic for gradient shrinking solid with harmonic Y tensor. It's a weaker harmonic. Y tensor is harmonic means the divergence of Y tensor is 0. So they also can get the same classification. So I have to go a little bit quick. Okay. So I would like to mention the recent result of steady soliton with this classification of done by Huaidong Cao and Chen Qiang. So I just put here, we have mentioned that the steady soliton, we have rotational cases of Seagar and the Brenner soliton. So we call here a conjecture is that in three-dimensional case, Brenner soliton is the only complete non-compact gradient steady soliton with positive curvature. You can see you have plenty of conditions, but it seems the conjecture should be proved. But it has been claimed by Perelman in his without proof. He claimed this is true, but without proof. So people try to work out the proof, but it seems that's not so trivial. So up to now, we have Huaidong Zhou and Qiang Chen proved that including actually they start with three-dimensional case. Even in we just look at the three-dimensional case of this result. If it is conformally flat, then it is either flat or Brenner soliton. So even in a three-dimensional case, you need the conformally flat. So it's different when you in three-dimensional conformally flat is a little bit different because y tensor is always 0. So actually, the most difficult thing is for three-dimensional case for this theorem. So the conjecture remains open. So how time I have? So actually, I just in the morning I have seen another result of them. In archive today, they claim that they can change the condition. The conformal flat can be implied by Baha flat. A Baha flat is a critical point of the norm. It's integral of norm of y tensor. So I will talk a little bit about the further questions. So the first question is, we have a point-wise scalar curvature estimate. Actually, we also can estimate the average of scalar curvature. But we want to know, because the volume is infinite, we want to know the average of scalar curvature decays to 0 at infinity if the curvature of course we need in which case actually we're wondering if the manifold is known with some, for example, with non-negative curvature, non-flat, it should be true or not. And another thing is that can we classify if you have a strict positive ridge curvature, then it not negative, but not strictly positive ridge curvature. Can you say that the universal cover split as a product, where the n has a positive curvature? That means if you have one direction with 0 ridge curvature, then the direction should goes to infinite. So you have a splitting. So the last question is, I just mentioned in the beginning, can you classify the generic gradient shrinking soliton? So it's just parallel to the recent result of coding and minicos for the mean curvature flow. In some sense, there are many similars between mean curvature flow and ridge flow. But in some cases, because the mean curvature flow, you have ambient space. You can. But for people who are working on the submanifold, you have an additional equations. Sometimes it takes the things easier. But I think it is an interesting question to classify the generic gradient shrinking soliton, because generic means the stable ones in some stability. With some stability. That stability should be modified a little bit, just not parallel to the mean curvature surface case. Thank you. That's all.